Lesson 1, Window Functions Introduction. Part 2, Window Functions Described. A window function is a function applied to a set of rows. A window is the term standard SQL uses to describe the context for the function to operate in. SQL uses a clause called over in which you provide the window specification. The over clause is where you provide the window specification that defines the exact set of rows that the current row relates to, the ordering specification, if relevant, and other elements. Absent any elements that restrict the set of rows in the window, the set of rows in the window is the final result set of the query. More precisely, the window is the set of rows, or relation, given as input to the logical query processing phase where the window function appears. But this explanation probably doesn't make much sense yet. So to keep things simple, for now I'll just refer to the final result set of the query, and I'll provide a more precise explanation later. The function used in this example is rank. This function calculates the rank of the current row with respect to a specific set of rows and a sort order. When using descending order in the ordering specification, as in this case, the rank of a given row is computed as one more than the number of rows in the relevant set that have a greater ordering value than the current row. What's most important to note is that conceptually the over clause defines a window for the function with respect to the current row. And this is true for all rows in the result set of the query. In other words, with respect to each row, the over clause defines a window independent of the other rows. This idea is really profound and takes some getting used to. Once you get this, you get closer to a true understanding of the windowing concept, its magnitude, and its depth. If this doesn't mean much to you yet, don't worry about it for now. I wanted to throw it out there to plant the seed. Part 3, Window Functions Explain. The basic way to think of how the rank values are calculated conceptually is the following example, expressed as pseudocode. Arrange the rows sorted by val. Iterate through the rows for each row if the current row is the first row in the partition. Emit 1 else if val is equal to previous val. Emit previous rank else emit count of rows so far. Part 4, Drawbacks of alternatives to window functions. Window functions have several advantages compared to alternative, more traditional, ways to achieve the same calculations, for example, grouped queries, subqueries, and others. Suppose that you need to query the VW order values view and calculate for each order the percentage of the current order value of the customer total, as well as the difference from the customer average. The current order value is a detail element, and the customer total and average are aggregates. If you group the data by customer, you don't have access to the individual order values. One way to handle this need with traditional grouped queries is to have a query that groups the data by customer, define a table expression based on this query, and then join the table expression with the base table to match the detail with the aggregates. Now imagine needing to also involve the percentage from the grand total and the difference from the grand average. To do this, you need to add another table expression. You can see how the query gets more and more complicated, involving more table expressions and more joins. Another way to perform similar calculations is to use a separate subquery for each calculation. Here are the alternatives, using subqueries to the last two grouped queries. There are two main problems with the subquery approach. 1. You end up with lengthy complex code. 2. SQL Server's optimizer is not coded at the moment to identify cases where multiple subqueries need to access the exact same set of rows, hence, It will use separate visits to the data for each subquery. This means that the more subqueries you have, the more visits to the data you get. Using window functions, here's how you address the request involving the detail and customer aggregates, returning the percentage of the current order value of the customer total as well as the difference from the average. And here's another query where you also add the percentage of the grand total and the difference from the grand average. Suppose that you want our calculations of the percentage of the total and the difference from the average to apply only to orders placed in the year 2007. With the solution using window functions, all you need to do is add one filter to the query. The starting point for all window functions is the set after applying the filter. But with subqueries, you start from scratch, therefore, you need to repeat the filter in all of your subqueries. Of course, you could use workarounds, such as first defining a common table expression, CTE, based on a query that performs the filter, and then have both the outer query and the subqueries refer to the CTE. However, my point is that with window functions, you don't need any workarounds because they operate on the result of the query. Part 5, a glimpse of solutions using window functions. The querying task I will address here involves querying a table holding a sequence of values in some column and identifying the consecutive ranges of existing values. This problem is also known as the islands problem. The sequence can be a numeric one, a temporal one, which is more common, or any data type that supports total ordering. The sequence can have unique values or allow duplicates. The interval can be any fixed interval that complies with the column's type, for example, the integer 1, the integer 7, the temporal interval 1 day, the temporal interval 2 weeks, and so on. Use the following code to generate the sample data for this task. As you can see, there are some gaps in the col1 sequence in T1. Your task is to identify the consecutive ranges of existing values, also known as islands, and return the start and end of each island. This query generates the following output. The next part is pretty straightforward. Define a table expression based on the last query, and in the outer query, group by the group identifier and return the minimum and maximum col1 values for each group. Now think of a sequence of 10 million rows, and try to translate it to the amount of work involved. The total number of rows that will need to be processed is simply enormous. The next solution is also one that calculates a group identifier, but using window functions. With this in mind, the following query returns the col1 values and row numbers based on col1 ordering. 1, col1, is a sequence with gaps, and the other, rownum, is a sequence without gaps. Within an island, both sequences keep incrementing by a fixed interval. Therefore, the difference between the two is constant. For the next island, col1 increases by more than 1, whereas rownum increases just by 1, so the difference keeps growing. In other words, the difference between the two is constant and unique for each island. Run the following query to calculate this difference. You can see that this difference satisfies the two requirements of our group identifier, therefore, you can use it as such. The rest is the same as in the previous solution, namely, you group the rows by the group identifier and return the minimum and maximum col1 values in each group. Observe how concise and simple the solution is. The solution is also highly efficient. Do you want to learn new skills in the fastest and most effective way? Visit learnwithvideotutorials.com.